So there is this massive multi-billion-dollar component of the renewable energy boom
Yeah.
that has like absolutely nothing to do with capturing sunlight.
Right. It's totally separate from the actual energy capture.
Yeah, and honestly, it's wild because if this specific component fails, your state-of-the-art solar farm instantly becomes just, well, it becomes a field of incredibly expensive shattered glass.
Oh, yeah. A complete disaster.
Because, when you drive past a solar installation or like look at a residential rooftop, you really only ever notice the panels.
Right. The glass.
Exactly. Those sleek, shiny rectangles get all the glory.
Yes.
But today, for this deep dive, we are looking right past the glass. We are zeroing in on the unsung physical infrastructure that actually makes solar power possible in the real world.
And it is such a common blind spot. I mean, for all of us, we get so focused on the photovoltaic magic, the actual conversion of sunlight into electricity, that we just sort of take the physical reality of the system for granted.
We really do.
You are putting these incredibly fragile, highly sensitive glass electronics outside, fully exposed to extreme weather for decades at a time. The underlying structure has to be an absolute engineering marvel, or the whole thing just falls apart.
Right. And understanding how that structural skeleton works is our mission for today's deep dive. So we are unpacking a really detailed March 2026 briefing from Eleanor Industries.
Yeah, they're a major player.
They're a massive extruded aluminium products manufacturer based in India. And the report we're looking at is called Aluminium Solar Structural Sections, Types, Uses, and Benefits.
And the timing and geographic focus of this briefing provides some really crucial context for you as the listener. India is in the middle of this massive surge in solar energy adoption.
Oh, absolutely massive.
They have highly aggressive national sustainability goals right now, coupled with a surging industrial demand for reliable power. But the core argument of this text, the thing we really need to focus on, is that you can buy the most advanced solar modules on the market, and your project will still be a catastrophic failure if the mechanical support system beneath them isn't perfectly engineered.
It has to handle the specific environmental loads of the site.
Exactly. The local wind, the weather, the topography, all of it.
Okay, well, let's unpack that engineering, starting with like the raw material itself. Because reading through this, the entire industry seems to have just universally agreed on aluminium as the gold standard.
Oh, yeah, without question.
When I was reading the briefing, it actually reminded me of the engineering behind a high-performance race car.
Oh, that's a great comparison.
Right. Because, like, the chassis of a Formula One car has this contradictory job. It must be incredibly rigid to handle intense aerodynamic forces and protect the driver. But it also has to be remarkably lightweight so it doesn't sacrifice speed. And you need that exact same strength-to-weight ratio sitting on top of your roof.
That is an excellent framework for understanding this. I mean, think about it. A commercial warehouse or a suburban house, it was mathematically engineered to hold up its own roof, plus maybe a certain amount of snow depending on where you live.
Sure.
It was not designed to support thousands of pounds of dead weight from a giant solar array.
Right. They didn't factor in a power plant on top.
Exactly. So aluminium provides the structural integrity to span these wide areas and hold heavy panels without requiring you to go in and reinforce the actual building underneath it.
Which would be hugely expensive.
Prohibitively expensive in most cases. But achieving that race car level performance isn't just about the metal itself. It's about how the metal is manufactured. And the text repeatedly emphasizes this extrusion process.
Right. And I think it's worth explaining the mechanics of extrusion here because it isn't just like cutting shapes out of sheet metal.
Not at all. Extrusion is this process where you take a massive billet of solid aluminium and you heat it up so it becomes malleable.
Yeah. But not completely melted, right?
Right, just softened. And then you use immense hydraulic pressure to force it through a custom-shaped steel die. If you picture industrial pasta making, where dough is pushed through a die to create complex shapes.
Like making macaroni or something.
Exactly like making macaroni. It's a very similar visual principle. But on a metallurgical level, something really crucial happens. When you force that metal through the die under all that heat and pressure, you are actually aligning the grain structure of the aluminium.
Oh, wow. So you aren't just forming a shape. You are fundamentally increasing the tensile strength of the material along the length of that specific shape.
Precisely. You are creating continuous, seamless geometric profiles that are engineered to bear specific directional loads.
That's wild.
You just can't achieve that level of structural consistency if you are just folding flat metal or welding pieces together. And because it's aluminum, you are getting all of this structural power while maintaining an incredibly light logistical footprint.
Which matters a lot for construction.
Huge difference. It's easier to transport, it's easier to crane onto a roof, and it is much faster for the crews to actually handle on site.
But weight is only half the battle, right?
Huh.
Because a race car goes back to a climate-controlled garage after a few hours.
True.
These solar structures live outside permanently. And the Eleanor text puts a really heavy emphasis on survival in harsh environments, specifically resistance to rust and corrosion.
And this is where the chemistry of aluminium becomes vital. If you build a frame out of steel and it gets exposed to coastal humidity or industrial pollution, it will eventually oxidize.
It rusts.
Right, iron oxide rust, and it flakes away. It literally eats into the structural integrity of the metal over time. Aluminium, on the other hand, also oxidizes when exposed to air, but it does something totally different.
What does it do?
It forms a microscopic, highly dense layer of aluminium oxide right on its surface.
Oh, so it basically creates its own barrier, like a permanent self-healing shield.
Exactly. It seals the raw metal underneath. That means these structural sections have a massive lifespan with practically zero maintenance required. You install it and it survives.
That's amazing.
Furthermore, the text points out the broader sustainability angle. If we connect this to the bigger picture, aluminium is infinitely recyclable without losing its metallurgical properties.
Right, so the physical infrastructure holding up your green energy is itself a fully sustainable material.
Exactly. You aren't permanently extracting resources just to build the frame.
Okay, so we have this lightweight, incredibly strong self-healing metal. How does that actually translate into the architecture of a solar installation? The text outlines the core components, like the 5 pillars of these systems, and I want to just quickly walk through how they connect together to form this skeleton.
Sounds good.
So if we are building this on a roof, you have to start with the foundation, which the report identifies as the rails and channels.
Right. The rails are the primary tracks spanning across the installation surface. And because of the extrusion process we just discussed, manufacturers can engineer these rails with built-in continuous T-slots along their entire length.
Oh, so like a groove you can slide things into.
Exactly. And this is a massive labor-saving feature. Instead of contractors having to drill custom holes into the metal while balancing on a hot roof, they can simply slide connectors anywhere along the rail.
That makes total sense. It provides the foundational geometry for the whole array.
Precisely.
Okay, so once the foundation is down, you have to actually house the glass panels. That brings us to the frames. And just to be clear for you listening, this isn't the mounting track. This is the physical metal border permanently wrapped around the edge of the glass module itself.
Right, it's the protective enclosure. Because a silicon solar cell is incredibly brittle.
It's basically a delicate sheet of glass, right?
Yeah. Exactly. So the aluminium frame provides the rigidity needed so the panel doesn't flex and snap during transport from the factory. It also seals the edges against moisture ingress, which would short out the electrical components.
Okay, so we have the tracks on the roof and the protective frame around the glass. Now, to connect them, the briefing highlights mounting brackets and clamps.
The modular connectors.
Right, and I have to admit, when I first read this, I was a bit confused. Like, I get the heavy rails and the large frames, but why does an industrial engineering report dedicate so much attention to clamps?
You'd think they're just basic hardware, right?
Yeah, it feels like an excessive amount of focus for literal screws and clips. Are they really worth focusing on?
It is very easy to dismiss them, but in structural engineering, the connection points are always the most critical points of failure. Think about the aerodynamics of a solar installation. A panel is essentially a 2-meter-long glass airfoil.
Oh, wow. I never thought of it that way.
Yeah, and when strong winds sweep across a roof, they create significant uplift forces trying to rip that panel away.
Literally like an airplane wing trying to take off.
Precisely. The brackets and clamps are the only things keeping that wing tethered to the rails. But it's not just about stopping the panel from blowing away completely.
What else is there?
It is about microvibrations. If a poorly engineered clamp allows the panel to shift even a single millimeter in high wind, that constant vibrating will transfer stress into the glass.
Oh, so it damages the internal components.
Yes. eventually causing microscopic fractures in the crystalline silicon. And those microfractures severely degrade the panel's ability to produce power.
Right.
So the extruded aluminum clamps are machined to exact tolerances to provide a totally rigid anchor neutralizing those vibrations.
That makes total sense. The connection hardware is literally acting as a shock absorber for the silica.
Exactly.
So that takes care of the rooftop setups.
But the text also details ground mount structures for utility scale farms, which obviously require a completely different approach since you don't have a building to anchor to. Yeah, ground mounts are the heavy-duty legs of the solar industry. When you are building a vast solar farm in an empty field, the terrain is rarely perfectly flat.
Right. It's full of hills and dips.
So ground mount extrusions are designed to be highly adjustable, allowing installers to establish a perfectly level plane of panels regardless of the rolling topography underneath.
Which must make scalability much easier.
Oh, absolutely. And they also elevate the panels high enough to manage vegetation growth and allow for heavy machinery to pass through for maintenance.
And for anything that doesn't fit neatly into a roof or a field, the briefing mentions a fifth category, custom extrusions, where manufacturers just design entirely new die profiles for unique setups.
Which is the ultimate advantage of extrusion. If a specific chemical plant needs a unique structural span with bizarre load requirements, you just machine a new die and press out the exact geometry required.
Okay, so we have a clear picture of the physical skeleton.
Yeah.
It holds the panels up, it protects the glass, and it anchors the system against wind shear.
Right.
But here is where it gets really interesting, because the briefing takes this fascinating turn. It argues that this entirely inactive, non-electrical metal skeleton actually forces the solar panels to generate more electricity.
It's a brilliant bit of passive engineering. To understand how that works, we have to look at the thermodynamics of solar energy.
Okay.
There is a very persistent misconception that because solar panels need sunlight, they operate best when they are hot. The physics actually dictate the exact opposite.
Wait, really? Why is that? I mean, I would naturally assume more heat means more energy.
Most people do, but it comes down to the behavior of electrons. A solar panel works by using photons from sunlight to knock electrons loose in the siliconite.
Okay.
That creates an electrical current. But that relies on a specific state of rest versus excitement. If the panel itself is physically hot from sitting in the baking sun, the electrons are already thermally excited. This reduces the voltage difference created when the sunlight actually hits them. So in simple terms, as the temperature of the panel rises past a certain point, its electrical efficiency actually drops significantly.
Wow, so it's very much like a high-performance computer.
Mm-hmm.
Like if I am running intense software on my laptop and it overheats the processor, intentionally throttles its speed to protect itself.
Yes, exactly.
In fact, I actually use an aluminum laptop cooling pad that props it up on an angle, allowing ambient air to flow underneath the chassis to pull the heat away and keep the system running fast.
That is the exact mechanism happening on a roof. A poorly designed mounting system will flush mount the panels tight against the roofing material, creating a trap for dead, superheated air.
Which bakes the panels.
Exactly. But the extruded aluminum rails are engineered to provide precise, calculated spacing between the hot roof and the back of the solar modules.
So the rails are effectively creating a dedicated wind tunnel.
Exactly. They promote natural convective cooling. Ambient air flows through that intentional gap, constantly pulling the thermal energy away from the silicon.
So by managing the temperature passively through the mounting structure, the electrical efficiency of the cells remains high.
Right. The skeleton is acting as a giant heat sink.
I just never considered that the structural mount is doing the thermodynamic heavy lifting.
Mm-hmm.
And the report also links the structural precision to maximizing sunlight exposure right.
Yes, through optimal alignment. The sun strikes the Earth at very specific angles depending on your latitude and the season. To get the absolute maximum energy, yield the angle of incidence. The angle at which the sunlight hits the glass needs to be mathematically perfect.
Right, you can't just slap it up there and hope for the best.
Not if you want peak efficiency. And because extruded aluminum does not warp or bend inconsistently, engineers can calculate the perfect tilt angle, and the structure holds it exactly there.
Yeah.
You aren't guessing on a roof. The hardware dictates the optimal orientation.
You know, when you combine the passive cooling, the vibration damping, and the perfect angle of incidence, it really shifts how you evaluate the technology.
It changes the whole paradigm.
It really does. Like, for you listening, if you are evaluating any technology, you can't just obsess over the active tech. You can't just look at the efficiency rating of the silicon or the software in the battery. You have to scrutinize the passive systems holding it all together, because that is what guarantees the yield over 20 years.
Without that robust passive support, lab-rated efficiencies mean absolutely nothing in the real world.
Completely agree. And speaking of the real world, the Eleanor text details exactly where all this infrastructure is being deployed.
Yeah, the applications are fascinating.
Right. It spans the obvious ones: residential rooftops, massive commercial and industrial factories.
Yeah.
But they highlight a specific application that I think really showcases the unique properties of aluminium.
The solar carports.
The solar carports.
Yeah, solar carports represent a major shift in how we think about land use. A traditional parking lot is just a vast expanse of dead heat-absorbing asphalt. By utilizing highly engineered, custom aluminium extrusions, developers can build massive elevated canopies over these parking areas without requiring incredibly bulky support columns that would interfere with the cars.
Because the aluminium is strong enough to cantilever outward and span those wide parking spaces while remaining light enough to not require massive concrete footings.
Correct. The strength-to-weight ratio makes it possible, so now you have dual functionality.
Which is awesome.
The canopy provides shelter, reducing the heat island effect of the asphalt, and keeping the cars cool, while the roof of the canopy is lined with panels generating massive amounts of localized energy.
So if this infrastructure is suddenly going up everywhere, from warehouse roofs to grocery store parking lots, where is the manufacturing base actually located?
Well, the report centers heavily on their home state of Gujarat in India.
Right, and that geographic focus is crucial for understanding the economics of this industry. Because the briefing doesn't just state that Gujarat is the hub, it explains the causality of how it got there.
What's fascinating here is that it is a textbook example of industrial synergy. It's a perfect storm of factors.
Let's break down that synergy. How does a region become the epicenter for global renewable infrastructure?
It started with proactive state policies. The local government recognized the solar boom early and implemented frameworks to aggressively subsidize and encourage renewable energy development.
Right, but policy alone doesn't build factories.
Exactly. Gujarat, and specifically the city of Ahmedabad, already had a historically strong manufacturing ecosystem, originally centered around textiles and heavy machinery.
So they didn't have to build the industrial mindset from scratch. They already had a workforce accustomed to operating massive factories and managing complex supply chains.
Exactly. They had the deep pool of skilled mechanical labor necessary to operate these advanced multi-ton hydraulic extrusion presses.
Makes perfect sense.
Add to that their proximity to major ports for importing raw bauxite and exporting the finished aluminium profiles and easy access to raw materials, you have a perfect storm. Ahmedabad became a center for leading suppliers.
Which proves that the transition to green energy is fundamentally a heavy industry undertaking. It requires vast factories, molten metal, and immense logistics.
It really does.
And as those factories in Gujarat pump out these materials, the technology is evolving. The closing section of the Eleanor briefing looks at where solar infrastructure is heading next.
Yeah, they note a major industry shift towards smart and modular systems.
Which makes sense.
It's largely an economic pressure. The actual cost of a solar panel has plummeted over the last decade. Today, the most expensive part of a solar installation is often the human labor required to install it.
Right, paying the crews on the roof.
So, to combat this, the industry is designing extruded aluminium structures that function almost like industrial building blocks. Highly modular components that snap and lock together rapidly on site with minimal tooling, drastically cutting down installation time and allowing for easy future scalability.
But if they are producing these perfectly machined, ultra-lightweight skeletons that can be assembled quickly, it feels like a waste to just bolt them down and leave them entirely static.
What do you mean?
Well, the sun moves across the sky all day. If the frame is that light and strong, shouldn't it be moving with the sun?
Ah, you've just deduced the most significant technological leap in the structural sector: integration with solar tracking systems.
That is just the coolest future trend.
It really is. Historically, solar arrays were static. You lock them at a fixed southern angle and accepted that they would only operate at peak efficiency for a few hours in the middle of the day.
But with tracking systems, the whole array physically pivots.
Right. They utilize precision-engineered aluminium structural components hooked up to industrial motors and sensors. As the sun arcs across the sky from east to west, the entire structural skeleton actively tilts the panels to directly face the light at all times.
Flattening the energy generation curve, so it produces maximum power from dawn until dusk.
Exactly.
But the physical stress of moving tons of glass and metal all day, every day, must be enormous.
It is. The shifting weight distribution combined with unpredictable wind loads hitting a moving target requires an incredibly sophisticated skeletal structure.
Right? The metal can't fail.
The metal cannot warp or bind up the motors. It relies entirely on the continuous structural integrity provided by advanced aluminum extrusion to maintain that fluid robotic movement over decades.
We have come a very long way from simply bolting some metal to a roof. We are talking about actively cooled, vibration-dampening, sun-tracking kinetic architecture.
It's incredible.
So as we wrap up this deep dive into the Eleanor Industries briefing, my takeaway for you is simple. The next time you see a solar panel gleaming in the sun, look past the shiny glass. Spare a thought for the highly engineered extruded aluminum skeleton underneath doing the invisible heavy lifting.
Doing all the real work.
Exactly.
Yeah.
It is quietly fighting off rust and corrosion, anchoring the glass against the wind, and channeling ambient air to keep the entire system thermally efficient. It is the literal physical foundation of the renewable energy transition.
I think that perfectly synthesizes the reality of the technology. And, it brings up a final provocative thought that I think builds on the fundamental properties of the metal we've discussed today.
Okay, let's hear it.
Well, the briefing emphasizes that these aluminum extrusions have an incredibly long lifespan and are naturally resistant to degradation. They are engineered to survive extreme elements for decades.
Right, the skeleton is incredibly durable.
But the solar panels themselves are not permanent. The photovoltaic silicon inevitably degrades over time. Usually after 20 or 30 years, their electrical efficiency drops to a point where they just need to be replaced.
Sure.
Furthermore, solar technology is constantly advancing. The panels available in 20 years will be vastly superior to what we install today.
Okay, I see where you're going with this. You have a skeletal structure that easily outlasts the technology it's holding.
Exactly. If these robust aluminum frames end up outlasting the actual solar panels they hold and can survive for 60, maybe 80 years, could the rooftops and vast solar farms of the future evolve into permanent modular grids?
Oh, wow.
Right. Imagine a scenario where the aluminum skeleton is treated as permanent civil infrastructure, much like a highway or a bridge. Every 2 decades, we simply slide the old glass panels out of those precision T-slots, recycle them, and slide the next generation of hyper-advanced plug-and-play solar technology right into the existing frame.
So we could essentially upgrade our massive solar farms as easily as swapping out a light bulb in a socket, because the structural foundation remains for generations and never needs to be rebuilt.
Exactly.
That is a brilliant way to conceptualize the future of infrastructure.
Wow.
Something really cool to explore and mull over. Well, thank you all for joining us on this deep dive. Keep looking past the surface and keep questioning the hidden structures holding up the world around you.